In this series of videos, I'm going to look at the concept of arrangements of lines, and then we're going to see an algorithm how to build this. So imagine that I have an input set of n lines in the plane. And when I draw these n lines, you can see that this set of n lines will decompose the plane into a bunch of regions. In particular, I have intersection points of the lines, which I can think of them as zero-dimensional object. I can look at the edges, and I can think of them as one-dimensional objects. I can also look at the regions created inside, which are essentially two-dimensional objects. Okay? Every point of the plane is included in one of these objects. Either it's on a vertex, in a line segment, or inside some region. Building this complex structure together with the doubly connected edge list that stores it is the problem of computing the arrangement of lines. Just to reiterate or to remind you, the doubly connected edge list will essentially create a vertex object for each one of these vertex. We'll create an edge object for each one of these, and we'll create a face object for each one of these faces. And then we'll set up particular pointers, and actually it will create two edges for every edge that are oriented in opposite directions. The edges inside will be in clockwise order, and then it will set up different pointers the same way that I talk about in the doubly connected edge list video. And once I have such a structure for this arrangement of lines, then I can do various operations. I can navigate, and I could do all sorts of nice stuff. But going from this input set of n lines to this complex doubly connected edge list structure is the problem that we want to solve here. One observation we can make is that this arrangement in the worst case could have n squared complexity. This is because, of course, every pair of lines can intersect, and therefore I could have omega n squared intersection points. And since this arrangement is a planar graph, it will also have omega n squared edges and faces on top of it. So in the worst case, this has n squared size. And there's actually an algorithm that can compute the doubly connected edge list that stores the structure in n squared log n time. And the idea is basically just use a sweepline algorithm. By putting a bounding box around them and clipping the infinite lines, I could just run a normal sweepline algorithm treating these lines as line segments. The sweepline algorithm will basically can maintain the doubly connected edge list, and the running time will be n squared log n. One question that you might have is that how do I find the bounding box? Well, that's actually not so difficult, because I could compute all the intersection in advance. Right? I could just run two for loops for I equals 1 to n, for j equals 1 to I, or 1 to I minus 1, and then compute the intersection of the lines I and j, stored in an array, find the maximum and minimum x and y coordinates, and that would give me the maximum, minimum y coordinates of all the intersection points. So therefore I could put a bounding box that just contains all the intersection points. So, and then I could run the sweepline algorithm. That would give me n squared log n solution, which is almost optimal. It's only a log n factor away from optimal. Another question is, since obviously I cannot do better than n squared time, can I remove this log n factor? The surprising answer here is that yes, it is possible to remove this log n factor, but it requires talking about the deep observation or deep lemma about the structure of a set of lines. This is going to be one of the first major discrete geometry results that we're going to see here, and probably the only major discrete geometry result that we're going to see here. And I'm going to talk about that in the next video.